Okay, guys. Couple things, housekeeping stuff. Don't forget your lab is due Thursday for you guys. Yeah. On Moodle, the way it's written is that it's due Friday, but it's actually due Friday at the first thing in May, right? About midnight. So it's actually Thursday night that it's due, not Friday. So that. Couple of things. There is going to be another quiz on today's topic on next week, so next Monday. All right. We're going to spend all of this class working on it and some of next class working on it. The Trump topics, I really find it important to quiz it because I want to force you guys to learn this part so that you're not leaving it to the last minute kind of on an exam situation or a test situation. There's also going to be another lab on that same day. Again, it's not a lab that requires a lab code, so you won't use that. There is going to be a voltage source this time, so it's not that bad. That's not any questions about anything going on so far? I have a question for you guys. On Moodle, when you guys go, I don't know how often you guys access it. Are things there pretty intuitive? Like, do you find it confusing the way it's laid out, or do you find it pretty okay? Okay, okay. Because you guys are group 1 out of 3, right? So this is where you guys see course recordings and annotations. Those are literally my voice being recorded while I'm teaching you guys. And the topics that are right on, that kind of upload as well. Everything else, yeah, everything else is, if it doesn't have a group number next to it, the problems are super important, okay? So I'm not going to tell you every single time, go and practice these problems, because I would say that way too much. It's going to be on your own volition, where you're gonna have to, once in a while, go there and do some work to keep up. Okay? It's really important to keep up with the practice. If you have any questions, to get those things sorted out. Okay? You won't know if you have questions unless you try the problem. If you find what we're doing in class really hard, the problems are actually harder, right? And we really only cover like the basic, like the theory behind it, and we do some basic problems associated with it. But the more in-depth problems, those ones come at home. You have to keep up with those. If you leave them until the day of the exam, it's gotta be out. Okay? Another thing I wanted to point out is I started this Adobe Connect page that you guys can connect to in case, I mean, this is a pretty small class and we're in here, so it doesn't really matter. But if let's say you can't see the board because whatever reason you're behind a bar, or you're behind someone who's really tall, or you can't see very well, you can go onto this page and connect to my desktop. So you'll see everything you'll see on your computer, everything that I'll see on mine. This also works remotely. You don't have to be necessarily here for that to work. If you're at home, because you're sick, because you're away on some sports thing or whatever, and you have some time you want to follow class, just go to that website and you will see everything that's happening on the on my screen on your screen. Okay, good. Okay, it's always going to be that link. So if you want, you can take that one into a bookmark it or whatever you want. It's going to be that way. All right. So now today's class. Today's class is our first really intense class. Okay, full disclosure, the other two classes end up rating me at the end of it. Hopefully get through it, and once I'll confuse you, and then we'll slowly deconfuse you. Okay? All right. I'm bound to the table today, so I can't walk around. It bugs me. But anyways. We did so far a point charge, and we did an electric field on a point charge. If this point charge here was positively charged, we would have electric field lines going radially outwards. Okay. I drew 8, but they're actually infinite numbers of electric field lines going outward, right? And they're all going in all sorts of directions. Now, there's really, other than electrons and protons, there really aren't all that much that are point charges. In real life, most things are non-point charges, and that's what we're going to deal with today. So let's say, for example, the most simple non-point charge object would be a line or a wire or something like that. Yes, it's going to have an electric field, and we have to know what does the electric field look like on a non-point form object. So we have to assume, this is our very most basic assumption that we have to make, is that this object is made up of many little points. So if I were to draw little points like that, it would look kind of like this, okay? And of course, it's more than just those that I drew. It's going to be an infinite number of point charges that make up a line. And if I were to give each one of those a drawing, electric field drawings, well, this one here, it says this was a positively charged wire. So we can see at this point, at this end of the wire, the line is going outwards. At this point, the line is going outwards. But what's happening above and below this, that's what's confusing. So if I were to arbitrarily take one here and say that there is electric field lines going in these directions, all right, then what I could also say is that there is another point charge here that will have the same kind of issue, same kind of drawing, right? And which one of these, if this was vector A, B, C, D, E, F, which ones would cancel each other out and which ones would be left remaining? If we're talking about just directions. A and C would cancel out, D and F would cancel out. And what would I be left with? What's that? Yes, I'd be left with a vector going up, vector going up. And you could generalize that for every single point between every single point that makes up this line. So you would have a whole bunch of field lines that go upwards like that. And the same thing would be true downwards. And then on the outer edges, then those won't cancel each other out. But we don't really care about those. We care about those ones in the middle. Okay? So you have something that might look like this. So far, so good? This, Zach said it a certain way, but I want to just make it a little bit more clear, okay? So he said that A and C cancel each other out, but that's not 100% accurate. Because let's say this one had a vector that way, and this one had a vector that way. Those two vectors would add up, okay? Because, you know, they're both going upwards. But this vector here and this vector here would be the ones that actually cancel each other out, all right? It's not necessarily the ones from the same point that will cancel each other. This was only possible because there is an equal number of charges distributed along this wire. So if I had a whole bunch of charges here and no charges here, then I wouldn't be able to do the same thing, right? So no charges here, a whole bunch of charges here, that'll give me a completely different field, electric field drawing for this wire. And that comes into our first layer of complication. In real life, things aren't uniformly charged, all right? Most of the time, they're non-uniform. And that's where our first complication is going to come up with. So let's talk about that. Second thing that we need to think about, and we need to understand, is this idea that we can figure out the charge of this wire if we can figure out how many charges there are per unit meter. All right, in the case of a length. So that means that there is something called a charge density that we need to take into account. Okay, so let's talk about that right now. So here I have another wire. It's not a rectangle, it's a one-dimensional wire. All right, so don't think of it as there is no height here. Okay, so it has a thickness. I drew a thickness, but there is not. Okay, so it's got it's like an infinitely thin wire that I just kind of blew up so you can see that I put positive charges all along this wire. You can see the distance between each positive charge here is about the same. So what I'm telling you by drawing this is that this is uniformly charged. Okay, so uniform charge density. Okay. If it's a uniform charge density and I take this delta L right here, I can tell you that in that delta L region, right, which let's call this 1 meter, let's call this delta L region 1 meter, then this delta L region, there's going to be two protons. You guys see that there's two, 1, 2, all right? So those are two protons in that one unit length of 1 meter. Okay? And because it's uniformly charged, no matter which 1 meter length I took, so let's say I took this 1 meter length, right, which is the same as that 1 meter length, if this is also delta L is equal to 1 meter, my charge is again 2 protons. And no matter which one I took, it's always going to be 2 protons. If I took it up here, if I took it over here, it will be 2 protons, right? And so let's do this situation. I want to ask you, what is the charge density of this wire? What would you tell me that it is? 2 protons? You got it. It's the length. Which length is that? How long is that length? Which is equal to? Yeah, L, but in this case, I'm talking about. So here I wrote it down here, I wrote it down here. 1 meter, exactly. So in this case, the charge density is going to be 2 protons per meter. Okay? And if I were to find out, and if I told you this thing was L, the big L is going to be 10 meters, right? And I told you that the charge density, which is the symbol lambda, is 2 protons per meter. What is the total charge of this wire? How would you calculate that? Is it? Exactly. So if it's 2 protons per meter, and I multiply that by the length, because it's 10 meters, my meters will cancel each other out, and in total I'm going to have 20 protons, and that's going to be my total charge of the wire. Okay? Very, very, very straightforward when it's uniformly distributed like that. Okay? I cannot make that assumption, however, if all of my protons were around here, and I had no protons around here, I couldn't make that assumption anymore because the distribution is no longer uniform. And we're going to talk about that a little bit later. It's not always going to be for a line object, right? Sometimes it's going to be for an area. Sometimes it's going to be for a volume, okay? So there's a charge density symbol for each of those cases. For linear charge density, we call it lambda, okay? For an area, we call it sigma. And this is all charge density. And for volume, we call it rho. Are those new Greek letters for you guys? Yeah, okay. And it's very simple. It's the amount of charge per unit of whatever it is. So if it's a length, it's charge per unit length. If it's an area, it's charge per unit area. If it's a volume, it's charge per unit volume. Okay. And then if you multiply that by, let's go back. In this case, if you multiply lambda by the length, you're going to get the total charge. If it's an area, you do sigma times the area, the total area, then you get the total charge of that whole area. And if the same thing for volume, if you have, if you multiply the charge density rho by its volume, then you should get the total charge. Right? It's all about finding total charge. Finding total charge. Okay. But again, it becomes more complicated when you're dealing with a non-uniform. That's what we're going to do now. So I'm going to talk a little bit about integral. Right? It applies to our previous example because it applies in every situation, including uniform and non-uniform charge density. And this is saying that if I were to take a wire, and if I had a charge density for that small region of that wire, all right, and we call that charge density lambda, and multiply it by dx, which is just the length of that small area, right? Then I'm going to get, if I do that, what am I going to get? If I do length times charge density, I should be able to get charge. Charge of what? Of the whole thing or just that small place? What's that? If I do lambda times that just small, that small area, then I'll get the charge of that small area. I'll get dq. Okay? And that's going to help me because if I integrate each side, I can get the whole q, right? So integration, for those who will have forgotten it, which is probably everyone at this point, the integration is when you add a lot of small parts, you get the whole thing, all right? So I'm integrating all the little lambda times dx's to get the whole charge, right? So the integral of dq, that's the most simple integral you can get, is always going to be q, or the total charge of the object, all right? And that will be, well, write it on the second. So that total charge Q is going to be equal to the sum of, or the integral of, all the lambdas multiplied by those small lengths. Okay? And if in this case lambda is a constant, so meaning it's a uniform density, and you'll know at one of your integration identities is you can remove constants from the integral, right? You can do that. And then if you integrate dx, well, that's also simple. It's just x. So lambda times x if it's a uniform charge density. Okay? And that's what you have written there. What would happen if lambda wasn't a constant and lambda was a function as a variable? Would I be able to take it out of the integral like that? No, okay, so that we're not allowed to do, okay? So we can only take constants out. So if my lambda was variable, was non-uniform, then it would be non-uniform as a function of the length of the wire, right? So it would be like x squared, for example, right? So if I were to say that lambda is equal to x squared, then that would just change everything, and you would have here, here you would have x squared dx. The integral of x squared dx is, you guys remember that? Okay, now fish guys, x3 over 3, okay? All right, so that's when your integration rules come back, okay? So let's do some problems like that, okay? And then the first one, let's do this one together. So I have a 2-meter long wire that starts at x equals 3 and finishes at x equals 5. Okay? And I'm asking you, I'm not even asking you about electric field, I'm asking you about the charge of this object. Okay? So the charge of this object, Q, is equal to the integral of the charge density multiplied by dx. So all the little charges, if you add them all up, I'm going to get the big charge. That's what I'm trying to do. And so I need to know that between the limits 3 and 5, right? That's where I got the 3 and 5 from the question. Okay? And in this case, it's very simple. Lambda is given to me. So integral of 3 times 10 to the negative 6 x squared dx, and then we just need to solve that integral. Okay? So if I were to do that, I'm just going to do it with you guys for this one. This 3 times 10 to the negative 6 is a constant, so I can say that, I can say that 3 times 10 to the negative 6 integral from 3 to 5 of x squared dx. And that's easy. You guys just told me that it's x to the 3 over 3. So it's going to be equal to 3 times 10 to the negative 6 x to the 3 over 3. And the limits are going to be 3 and 5. You guys remember this notation? And how do I solve that? You guys remember how to solve that? Roughly? How would you do it? Just remind someone, help yourselves out. Elizabeth, how would you do it? Exactly. All right. So what you need to do to solve this integral is plug in 5 into this function, subtract when you plug in this to the function. All right. So it'd be 3 times 10 to the negative 6 times 5 cubed over 3 minus 3 times 10 to the negative 6 times 3 cubed to the power of 3. Sorry, 3 to the power of 3 over 3. And that'll give you an answer, which I don't know. You guys have to. Someone have a number for me? Cedric? 9.8 times 10 to the minus 5. Did everyone get that? What are my units? Coulombs. Very good. Coulombs. Let me ask you a different question. What if I were to take those same 2 meters but instead of it being between 3 and 5, I made it between 8 and 9. Would that change your answer, yes or no? It would change your answer, all right? And let me ask you another question. If I were to draw this function, right? So it says lambda as a function of x is a quadratic formula, so it should look something like this, right? And if we're taking the integral of this function here, what we're doing is we're measuring the area underneath it, right? So this is the area underneath between 3 and 5, and here's the area between 8 and 10. Which area is bigger? Between 3 and 5 or between 8 and 10? So are you expecting the integral for this with these limits at the bottom to be greater or less than the initial one that you calculated? Greater than. Okay. Can you just, for practice sake, calculate what it would be between 8 and 10? Did you get something? Understand to the units? Cool. Did everyone get that? It makes sense. It's greater than the one that we did before. So it seems good to me. So remember the tool, this integration tool is really important. Find the charge of one small place and then add them all up to find the charge of everything. Okay? We're going to use that again right now. Okay, so what is the magnitude and the direction of the electric field at 1 meter to the left of the wire? So you have this point here, we're going to call that point P, all the way on the left, and it's located 1 meter away, right? So that distance there is 1 meter from this 2 meter long wire. And I want to know what the electric field is at this point. I want to know what the electric field at this point is, all right? So remember, how did we find the electric field again? What was the formula for it, first of all? That. Yeah, exactly. So if you remember, electric field was KQ over R2. And if that's this line, this entire line here, from here to here, right, this line here, instead of it being a full line, let's call it 2 points, all right? So if there was a point here at the beginning and a point at the end, and they were both negative 4 coulombs or whatever, we would ignore the numbers for now because they're irrelevant, and they were both negative 4 coulombs, then at this point, you would have an electric field due to this first point here, and you would have an electric field due to this point, and so you would have an electric field going in that direction. All right, does that kind of ring a bell if you had 2 points? Yeah, no, but it's not that simple. It's not just 2 points, it's a million different points, right? All of which add up to a charge of negative 4. So what we need to figure out is how do we add up all those charges? Because the points, as many as there are, all of their distances are increasing, right? And as distances increase, they provide less electric field. So for example, this last point here will provide a smaller electric field to point P than the points right at the beginning, all right? And the same thing for the middle. The middle one's going to give less than the last one, but more than the first one. Sorry, less than the first one, but more than the last one. And so we have to add up all of it. So best thing to do in this case is to use integration. To use integration, we can find the electric field that one of these points will give, add them all up, and that should give us how much the electric field is for everyone. Let's start with that. Okay, so here I'm telling you that there is a point P that has a small electric field, dE, right, caused by this charge that we're going to call dq, okay? And the distance between P and dq is this distance d plus x, and in this case, d is given to you as 1, so let's call it just 1 plus x, right? And so we know that dE, so the small electric field that you're going to feel from that small 1 dq charge is going to be k dq over 1 plus x squared. Okay, so far so good. But this doesn't work out for us because dq is a function of q, and our denominators is a function of x. So how could we change that? We know that charge density. Yeah, Elizabeth. So what I said before is if we find how much electric field we get from one small point along this wire, and we add up all those points, we can get how much electric field you get from every point along that wire. Okay, so I'm finding, so this formula is just showing me how much electric field am I feeling from just this one point in that wire, not the whole thing yet. Yeah, okay. So, but we don't have dq as a function of x yet, so we have to remember one thing, is that if we go back, we know that lambda is equal to, or dq rather, is equal to lambda dl, or in this case dx. So that means that if I take the charge, oops, if I take the charge of this whole wire divided by its length, which is given to us, so a long 2-meter wire holds negative 4 microcoulombs, right? That means I can figure out what lambda is, right? So negative 4 microcoulomb divided by 2 meters gives me negative 2 microcoulomb per meter. That's my lambda. Correct? And then we know also that dq is equal to the charge density times a very small part of this wire. So now we can replace that in here. Now, the electric field of a very small point is going to be equal to K times the uniform charge density, linear charge density. It's uniform because we just assumed that it's going to be equally distributed all throughout, multiplied by the small region that we're talking about, divided by 1 plus x squared. Now we want to find the entire electric field. So the only difference now we need to do is just integrate both sides to find the entire electric field. So the integral of dE, well, that's just E. Then we have the integral from 0 to 2 meters of k lambda dx over 1 plus x. Which of these letters are going to be constant that I can remove from the which one? K and lambda, exactly. So k lambda integral 0 over 2 dx over 1 plus x squared. Do you guys remember how to do an integral of this kind of polynomial? Maybe if I rewrote it in a different way, it might make more sense to you. So k lambda integral of 0 to 2 of 1 plus x to the power of minus 2 dx. You guys remember how to do that?
So it's the same rule. Yeah, exactly. Yeah, because you're adding up all the charges from the beginning of the wire to the end of the wire. If I were to continue here, you would get that the electric field is equal to K lambda of minus 1 over 1 plus x between 0 and 2. If you do the integral properly and you do the calculations, you see that you get 2/3 K lambda, which is 2 over 3 times 9 times 10 to the 9 times, and we said our charge density was how much? Yeah, 2 microcoulomb per meter. And that'll give us our electric field. Someone, can you do that over? Yep. Is it 1/1/3? So if you plug in the 2, it'll be minus 2 over 1/3, over 3. Yeah, but it's 1 plus 2, right? So minus 1 over 1 plus 2 minus 1 over 1 plus 0. So it would be 1 negative 1/3 plus 1 equals 2. Okay? You guys still have your integration identities from last year and like on the cheat sheet, so is that what that is? Or your Cal 2 paper? So here's what I propose, and I haven't talked about it with the other class yet, but I did talk about it with the other teachers. For the first test, I'll give you guys the integration tables, all right? The different tricks. So integration for polynomials, integration by parts, by substitution, the trig identity. I'll give that stuff to you guys, all right? But technically, you should have already passed that course. So in the second test and on the exam for sure is going to be nothing, no A's whatsoever. But for the second test, I'm just going to take away some of that. It's kind of like a gradual decrease. Okay. Does someone have a number for me? You have to convert the micros into regular coulomb. It's electric field. So for electric field, what would it be? What were the units for electric field, guys? It was what? It wasn't coulomb. Coulomb is charge. What's that? Newtons per coulomb, exactly. Well, what's the number though? I need to know the number. It could be negative. Come on. Moins 12,000. Did everyone get 12,000? Yes, no? Yeah? All right. So far, so good? It's complicated, I'm sorry, I know. It'll get easier with more practice for sure, and that's what we're going to do a little bit later. Let's do one more example together. This one is going to be a little bit more complicated because now we're dealing with volume, all right? And it relies on us understanding how to calculate the volume of the sphere. I'm just going to let you guys read the question, then we'll work parts of it together, and we'll just read it first. So let's try to dissect this question, okay? What's really important here is to not get confused by it. Okay, getting confused by it, automatically you're starting at a disadvantage. So there's two things being written here, all right? And we have to decipher that. That looks so complicated, but it's actually really not. It's telling you that this, by the way, this key is rho. There was no rho button on the keyboard, so they used just P. But rho, or the charge density, is equal to 0 when you're looking at a distance outside of the sphere. So the sphere has a radius of capital R, right? So the sphere is no longer a sphere outside of this sphere. And so anything that's outside of that sphere, but any distance bigger than the radius of the sphere, charge density is 0. Okay. Now that's it. We don't have to look at this line anymore ever again. Okay. Now this line here, this is telling you that the charge density in the sphere, so anything at any distance less than the radius of the sphere, the charge density is equal to this function. Okay. And this function is a function of r, which is the radius of the sphere. Is at a distance from the center of the sphere. Capital R is the radius of the sphere. And that doesn't change. So that's actually a constant. Okay, so all throughout this problem, this big R is a constant. We don't need to deal with it in terms of a variable, but it does vary as a function of the distance from the center of a sphere. So now we need to figure out, how do we break down a sphere into different radiuses? So how would you guys do that? If I had a sphere, a 3D sphere, I can't really draw that here, and you were to break it down into something as a function of R, how could you break it down? I'll give you a hint. Think of onion. Many layers, exactly. All right. So maybe my onions hint was too obvious, but that's exactly how you need to do. How you build a sphere is if you have a lot of little thin shells and you place them one next to each other. So this sphere has a center, right? And this center, how far is that center from the center? What? 0, okay. This distance is 0 from the center. And this distance here is going to be r. All right, and then in between all this, in between 0 and r, there's all sorts of concentric, hollow, very thin. I'm trying to say very thin shells. Right? That's what we need to understand from this. Okay, now let's move forward. So the question is asking you, what is the total charge here? So again, dq is going to give us the charge of one of those shells, all right? So dq is equal to rho times the volume of one of those shells. So far, so good? I'll give you some chance to practice this in a moment. Okay? So dq is equal to rho dv, all right? And, whoops. And so let's write down what rho is, and let's write down what dv is. So dq is equal to rho, which is equal to 4 times 1 minus 4r over 3 capital R times dv. how could we break down our giant sphere into something dr? Because look, the variable in this question is little r, right? The distance from the center. So how could we end up with something dr? You guys remember that a little bit from Calc last year? What's the volume of a spherical shell? Close. 4 pi r squared. Okay? So if you take, I'll explain what I mean by this. So I wrote down that 4 pi r squared, this is the area of one sphere, right? So imagine any random one of these spheres, you take the area of it, and you multiply it by its radius, then you should get a full sphere, right? So here you have the area of a sphere multiplied by the thickness of that sphere, and it's a tiny, tiny thickness, right? Infinitesimally small thickness. And if you multiply that by the charge density, then you get the charge of that infinitely thin shell, right? And now we just have to integrate it to figure out what the whole charge is. So then you integrate both sides, so you get Q is equal to the integral of, and we're looking at from the center to the edge of the sphere, so from 0 to r, of 4 times 1 minus 4 over r over 3 capital R times 4 pi r squared dr. There's a whole bunch of constants in there that we can take out of the integral and make this super simple. So what I would write down is, if I were to take out all the constants, Q is equal to the integral of 0 over r, and all the constants are 4, 3 over r, so this 4 here, this 3 over r, and these 4 pi. So it'd be 16 pi over 3r, that would be the constant. 16 pi over 3r multiplied by, and then it's going to be, if I distribute this r here like that, it would be r squared minus 4r cubed dx. Oh boy. 4r cubed. Okay. Now, we're still in physics class, and I still anticipate you guys to understand this part the most. If you can get up to here, I'm okay with giving you like 95% of the mark. All right. Really, that's the hardest part, is to just setting up the integral. All right. If you can set up the integral, that means you've done all the work. And if you made a mistake after that, it's probably because you messed up some Cal 2 math that you weren't able to get properly, or you forgot, or you made a stupid calculation mistake. So I don't really care so much about that. It's important if you want to get full marks, but let's be real here. Not everyone's going to get it. It really is a matter of establishing that integral. All right. So if you get up to here, consider yourself that you've understood this topic. Okay. I want you guys to practice that. This is a little summary of what I just talked about. I want you to practice that. On Moodle, there is a document called Problems-Charge Density. Let's do that for 20 minutes. All right. And if you can do the whole integral process. But what I really want you to focus on is work everything up until establishing the integral, and then move on to the next problem. Okay. And some of them are not going to have. Some of them are going to be uniform charge density, so you won't even have to do integrals in some cases. All right, so let's take 20 minutes to do this. This is also your break time, okay? So I'm going to go at 35. I'm going to start right away the next topic. All right, so if you need a couple minutes, take a nap, but I also want you to work on this problem. Yep. Wait.
Yeah, exactly. Yeah, that's correct. We can do that. You guys get cold or something? All right. So this new topic is, so we found out the electric field of 1, 2, and many point charges. We find the electric field of a line of a flat surface. Now we're going to do, what about 2 flat surfaces, parallel plates. And I chose this one specifically because I could have done 2 spheres, I could have done a million point charges, I could have done anything. But this one specifically I chose because it's very important to your life. Right? You guys use it a lot. What do you guys notice up here? Do you guys recognize what this is? What is that? DNA? What about DNA? What is the thing called? Like, that's why you would use it, but what is the thing that you're using? Kind of weird plastic? It is some kind of weird plastic. What is it called? You guys remember what it is? It's what? No. Gel. Okay, that's the first word. What? Starts with an A, that's very good. Starts with Aragos. That's not a word. Agarose. Do you guys remember that? Gel, agarose, electrophoresis. That's what it was. Can't you guys remember that? But it is actually quite important. In biology, you use this a lot. Like, if you're, one day you guys will be doing your master's and PhD, if you're in any biological field, any biology really, you'll be using that like 10 times a day. And you kind of get really automatic on how to prepare them, how to load them, how to run them. They operate on the principles of electric field, right? And if I were to show you what this is, to give you a little bit more detail, maybe remind you a little bit how it works. This gel here, I mean, it's really small. Maybe I can zoom in. Can you do that? Okay, yeah, look. If you look at it really carefully, there are these wells here. Okay, it's not letting me write on it when it's zoomed in. Right, there are these wells here. Do you guys remember those wells? And how you have to inject the DNA with those micropensetters into those wells? You have to be really careful because if you went in too deep, or not deep enough, it would just overflow everywhere and you would lose all your DNA. Okay, so you're injecting your DNA there. In this case, this gel has 2 layers, all right? And the DNA is flowing
downwards like that. Okay. Tell me something about DNA. What is DNA made of? The other two classes had a really hard time. I hope you guys remember. Yeah. Glucose? You're right about it's a ose, something ose. It's a sugar. What's not glucose though, but you're close. What does it stand for? What does DNA stand for? What does it stand for in French? This is actually a ribo. The ribose is for the ribose sugar, okay? But it's okay, Zach. You said the most important part, which is the other thing. What was it? It's not phosphorus, it's phosphate. What is phosphate? Now, can now go back to your Gen Chem or grade 11 chemistry. What is phosphate? What's that? PO4 3 minus. All right, so PO4 3 minus is phosphate. And DNA, if you guys remember, is made up of a whole bunch of these phosphate molecules, right? So you have this, remember the phosphodiester bond? You guys remember that? Barely? Am I bringing back nightmares? PTSD in biology? If you guys remember, there's a double helix, right? And there's these bases that connect to each other, right? Like this. And let's say I called one of these units a nucleotide, right? And this is another nucleotide. The connection between them is called a phosphodiester bond. And in that connection, there is that phosphate molecule. All right, so you have some phosphate molecule. And can you tell me about this particular phosphate molecule that might be important for electricity magnetism that we're talking about right now? It's charged, and it's charged how? A negative charge. Okay, good. It's a negative charge. Okay, we use that in these electrophoresis gels, and that's why it's such an ingenious and so simple. I can't believe I didn't think of that method. Right. So here's what they do: they apply an electric field, just like that. In fact, actually, you guys are going to tell me because I don't know if I drew that correctly. If I want the DNA to flow downwards, right? What's going to be the charge of the area up here? Plus? It would be, I want the minus stuff which is in those wells to flow down. So I want to repel the phosphate. So is it plus or minus? Minus. Okay, yeah. So it's going to be a whole bunch of minuses there, and it's going to be a whole bunch of pluses here. And you're going to apply this, if you have all these charges there, if you have all these pluses down there, all these minuses up there, then you're creating an electric field, right? So which direction is the electric field? Going downwards or going upwards? Remember our convention of electric fields. They start where and they end where? Positive to negative, exactly. So my electric field is actually going to go like that. All right. But because DNA is a negatively charged molecule, it's going to go opposite of that direction. Because remember, the electric field only dictates where a positively charged particle would go. So DNA is a negatively charged particle, so it's going to go in the opposite direction. So that means if you put DNA, there's going to be a force pushing it downward, and it's going to migrate. And the gel matrix, so that powder stuff that you microwave with the buffer and all that stuff, that is going to make it so that different size molecules will travel at different speeds. So the really big fat ones are going to be slow, and the really small rapid ones are going to go further, okay? And therefore you can separate your DNA based on size. Now this works because our electric field, if you notice, is totally parallel at all points, right? If I were to do it differently, and just put 1 point charge there and 1 point charge here, yeah. Okay. Okay, I'm just gonna wait. Not liking me right now. I think I'm doing too many things with the computer. I got the video capture thing going on with the chat room, with the Adobe Connect and the PowerPoint all going on at the same time. Oh, there we go. Okay, perfect. So if I have just one positive charge at the bottom and one negative charge at the top, and I loaded all my DNA along these wells, how is the DNA going to migrate? Mark, what do you think? Yes. It's going to go outwards, you think, like that? If I have a piece of DNA here, where is it going to get attracted to? Margot, you want to give another try? Where's it going to go? If I have a negatively charged piece of DNA there, where am I going to get attracted to? Yeah, say it. Across to what? Exactly. So the piece of DNA is going to go straight there. What about the one that I loaded into that well? Where is it going to go? Same place, right? So instead of getting nice parallel lines, I'm going to get this, and this piece of information is going to be garbage to me. I can't compare the sizes from one lane to another. So it's really important to have a uniform parallel electric field. Okay, so that's where the parallel plates come in. So the machine that you guys use had a parallel plate. That's one of the plates. That's the other plates, and then you migrated stuff in between. Another use of the parallel plate electric field is anatomy. Was it Nurse Jackie now? I think is important. If you're really old school, you watch ER. The point is, in those shows, a lot of the times you'll see them doing that, and they shock you. You know what I'm talking about? Those are the use of parallel plate electric fields, right? So those are the parallel plates, and what you're doing is you're creating a voltage differential between the two panels, and current's going to go, a really strong current's going to go from one end of the panel to the other, passing through theoretically your torso, which will refibrillate your heart back to animation. Now in those shows, what's really fake though is that they charge you like 6 times. You're like, damn it, it's gonna work, it's gonna work. And then after like the 8th time you survive, no. you're basically, it has to be that your heart just stopped and you give them one shot, and if it didn't work, let's try something else, what they call it. But anyways, they do use that. That is an example of a parallel plate electric field. There is like air purifiers. You guys definitely have those at home. Those are all using parallel plate electric fields to absorb charged particles of air molecules that pass through. That's basically everywhere. Capacitors that flash in your camera, electric field, parallel plate electric field. So essentially, super duper important. You might see them in circuits. They look like that in the circuits, and we're not talking about circuits today. 3 weeks time, once we start doing circuits, capacitors will be your worst enemy. And here we have like the classical representation of parallel plate electric field. Okay, so here it is. There's a negative end of it. There's a positive end of it. And what this is doing is that it's creating a uniform electric field where all the lines are totally parallel to one another. Okay, that's the important part of it. Okay. I'm mentioning voltage today, but I'm not officially introducing voltage to you until possibly next class. Okay, so take it for what it is for now. Essentially, what I'm talking about is if this is a negative charge and this is a positive charge, and this has got a negative voltage, we're going to call this voltage B, and we're going to call this voltage A, then the difference of voltage potential between the two, or the voltage difference between the two, delta V, would be equal to VB minus VA. Okay? I don't expect you to totally understand that right now because we haven't talked about voltage yet. Let's take it for what it is for now. If there were more positive charges here, added more charges here, and added more negative charges here, is my voltage difference going to increase or decrease? So that's your slide set. So I have more, now I have put more charges compared to before, more negative and more positive. Is this delta V, is it going to be a bigger difference or is it going to be a smaller difference? Or is the difference not changing at all? What's that? Not changing? Who says not changing? Who's just putting up their hand because others have put up their hand? It's not changing. The voltage is changing. But how is it changing? Do you think there's going to be a strong? Think of this as a charged paddle. All right. So I have, let's say, positive Q in one paddle, negative Q in the other paddle. All right. Is that going to be stronger or weaker compared to if I had 10Q in this paddle and negative 10Q in this paddle? What's going to be stronger? What's that? The 10Q. And there's more charge, there is more potential difference between those two paddles. So charge is also an important thing. I'm going to explain to you how that works. This formula here, I'm going to explain to you. Once we do circuits. I'm going to ignore it for now. But what you need to know right now is that this electric field, right, is proportional to the voltage. Okay, so the stronger the voltage, the more electric field lines I can draw in between them, the stronger they're going to be. If I take these parallel plates and stretch them really far apart, is the electric field going to increase or decrease? Going to decrease, exactly, right? So that means that the greater the distance, the lower the electric field. So that means it's divided by R, it's inversely proportional to the distance between the two plates. Okay? So the electric field is proportional to voltage and inversely proportional to the distance. Okay? That's important. Let's talk about force too, because that's important. We just talked about electric field, right? And if you remember from, is it last class or 2 classes ago, when we introduced electric field, I said that force divided by Q is equal to electric field. You guys remember me talking about that roughly? Okay. I mean, if I rearrange this, I can also say that force is equal to Q times the electric field, right? I just sent the Q upwards. I just made a little algebraic thingy. So force is equal to the charge times the electric field. And any force is always equal to acceleration. I'll explain to you why I mentioned that right here. But before I move on though, what did we say in the last slide electric field is equal to? Going back, what is it equal to? Gabriella? Exactly. So I can actually also replace that here. I can say that Q times delta V over R is equal to A. So that might be useful later when we're doing some calculation. Okay. Now let's say I have two parallel plates. And there's a positive end of that plate, right here. Parallel plates, there's a voltage differential, there's a distance between them, and I put a proton right there. So that's the proton. What's going to happen to this proton? I'm just going to draw it a little bit higher. I have a proton. What's going to happen to this proton? Cedric? It's going to go towards the bottom. If it goes towards the bottom, that means there's some kind of motion, right? And if there is a force that's causing this motion, is this velocity of this particle, is it going to be constant or is it going to be changing? Changing, which means that there is an acceleration. And that acceleration is measured by this A here. Okay? So you have this proton that's going to move in that direction with acceleration A. Therefore, its velocity is changing. This should trigger your memory a little bit because I'm again taking you back to mechanics when you guys did projectile motion. You guys remember projectile motion? Right? It didn't have to be projectile motion, but it was basically non-uniform motion, which means that the velocity is increasing or decreasing or whatever. So if I put a proton there at rest, it would slowly and slowly gain a velocity and accelerate towards the other end of where it's attracted. So let's do some very quick and painless examples until we get to the more painful examples. So this one's super easy. You have a capacitor who has a voltage of 330 volts, and the distance between the parallel plates is 9 meters. How do you find the electric field? Nine millimeters. First of all, how would you do it? Say that, Elizabeth? Exactly. So E is equal to delta V over R is equal to 330 volts over 9 times 10 to the negative 3 meters. Could you give me a number for that? What are my units? Newtons per coulomb. But now we can define a new unit for it, right? Volts per meter. Exactly. So far, so good? That was like Bobo level, you know. Let's do something a bit harder. All right. So a proton is accelerated from rest from the positive plate inside a parallel plate apparatus. The plates are 3 centimeters apart and connected to a 110 voltage source. What is the final velocity when they collide? So let me just draw you a little diagram. So here you go. There is the positive side, there's the negative side, there's a proton, so a positive charge right there at the start. And when you turn this machine on, this proton is going to get launched in that direction. The distance between here and here is 3, well, times 10 to the negative 2 meters, right? Or 0.02 meters, 0.03 meters. And I'm asking you, what is going to be the velocity at the end? All right. And automatically, when I talk about velocity, you should think of two things: one, kinetic energy; two, kinematic. Right? You guys know the term kinematic? What is it in French? Kinematic? Yeah. Okay. Yeah. So that's what you would think about. In this case, because I'm talking about acceleration and all that stuff, you would think about kinematics. Okay. So that means we need to find acceleration, and we had an expression for acceleration before because we said that QE is equal to ma, right? Which also translated to Q delta V over R is equal to ma. And if I wanted to find A, I just isolate it. So it'd be Q times delta V divided by Rm. Now, what's Q in this case? It's not directly given to you, but it is actually given to you. It's one proton. So the charge of one proton is what? You guys remember it? Yeah, exactly. All I hear, by the way, when you guys say that is, but I'm assuming you're saying the right thing. 1.6 times 10 to the negative 19 what? Coulombs. Okay, very good. So Q is equal to that. And mass, what is that the mass of? It's the mass of the object that's being launched. What's the object being launched? It's what? It's a proton being launched, and a proton has a constant mass that we can easily Google. The mass of a proton, if I'm not mistaken, actually, someone look it up. I don't want to make a mistake. It's something times 10 to the negative 27 kilograms. But I don't remember. It's what, 1.67? Come here? 1.67? Let's just say 1.7. So there you go. The mass of a proton is 1.7 times 10 to the negative 27 kilograms. Okay? And therefore, we can find the acceleration. Yeah, Elizabeth. R times M, yeah. Yeah. Essentially, if you look at this line here, right? It's, if I just took the M and shot it over to the other side. Once I have acceleration, which formula could I use that relates initial velocity, final velocity, acceleration, and displacement, because I have the displacement? Which formula can I use to establish that relationship? You guys remember it? You should know this better than your biology because it was sooner than your biology. What? V you could use that one, but we don't have time right now, and we don't really care about time. So you could, that one would help you find time. There's the other one. There's only one other one, guys. Vf squared is equal to V initial squared plus 2a delta d. Okay? We have the initial velocity at 0. We have the 2. We have the acceleration, we just calculated it. And we have the distance between the two plates, because that's how far it's traveling. That's all you need. Solve for Vf, get a number, boom, move on. Okay? Something. So we move on. Do you need to know exactly what that number is? I'm okay with you understanding it up until now. Plugging into a formula. Yeah. Yeah. The delta D, in case you're asking, is 3 centimeters, okay? Because it's traveling from one plate to the other plate. This is the same question, except this time the proton doesn't start at the positive end, it starts somewhere in the middle. So the proton starts there. And this is 1 centimeter. Okay? The only difference here is that when you're doing your Vf squared is equal to Vi squared plus 2a delta D, your delta D, instead of it being the whole distance between the plates, just going to be 1.0 centimeters, or the distance at which it traveled. And it's not super terribly complicated. You're going to get another one. Okay, good. Okay, so here we're getting to something called cathode ray. Did you guys? Not sure how young you guys are, but do you remember not having flat screen TV? Yes? Oh, okay, great. So I don't know. I taught high school last year, and just to give you an idea, my oldest students were born after the year 2000. That's just depressing. That means that 90% of my students didn't know what 9/11 was. You guys know that? All right. I'm going to ask you guys something. Up until now, Let's say I took an electron here. Okay. Let's say I took an electron here and let go of it. All right. Or let's say I took an object above her and I let go of it. What's going to happen to the object slash electron? What's going to happen to the object? You tell me first. That. It's going to fall. It's going to go. It's going to fall. Perfect. And if I were to graph its y position as a function of time, what would it look like? Straight line? What is it going to look like, guys? The parabolic function, right? So it's actually going to look like this. Over here, there's an electric field upwards. But because it's an electron, this object is going to fall downwards, right? It's going to get attracted downwards. It's going to slowly accelerate until it hits the ground. And if you were to talk about its position on the y as a function of time, it's going to look the same exact thing. Okay? Kind of like if you were to drop an object between parallel plates, and that object had a charge, then it would get attracted downward, it would accelerate down. Okay, that's one point I'm trying to get you guys to make a parallel here. Now, that's if I had dropped it. What if I had Earth and an object, and I launched it in that direction? What is the object going to do? Yeah, so initially it's going to go that way, but as time increases, it's going to increase its y velocity because there's an acceleration downward. So it's going to go like this, it's going to go, and it's going to eventually it's going to fall, and that's that. If I said this is VI, and I took this position here, and I broke down its velocity, there's a y velocity and an x velocity. What could you tell me about VI here and Vx here? They're the same. Why is it the same? Why? Yeah, there is no acceleration on x, the velocity doesn't change on x, and the velocity does change on y. Okay, so ax is equal to 0. Perfect. And if I were to take an electron and shoot it in this direction, what's going to happen to it? It's also going to do the same thing. Correct? It's like a projectile motion. Except now acceleration, instead of it being the acceleration of gravity, it's the electrostatic acceleration. Okay? What if this is really short? What's going to happen to it? Ah, yes. Okay, so if this is really short and never hit the actual plate, I would actually do that and then move on forever. Right? Unless there's other external forces acting on it. But we're assuming that these are the only forces acting on something. Okay, so here's what this is. It's a beam deflection apparatus. So you have this beam that's going in this way, right? So there's your parallel plates there, parallel plate, parallel plate. You have your beam going in between, and it's getting somehow deflected from that parallel plate through exactly that phenomenon. Okay. Now, if I have a parallel plate, okay, if I have a parallel plate like this, right? I just need your help, Valerie. All right, so if I have a parallel plate like this, and I shoot a beam here, it's going to get deviated in the up and down direction or the left and right direction. Up and down direction. All right, so I can change based on I can control this voltage difference here. I can change how much it gets deflected here. Or maybe like this one, right? And if I were to have parallel plates like this, do I modify its up and down direction or its left and right direction? Left and right direction. So if I have this like that and another parallel plate over here, so we can and I have this set up here. What I can do is I can control my photon's direction both in the x and y coordinates in 3D space. You guys get what I'm trying to say? All right, now at the end of this, there's a screen in which you're projecting these photons. So if you were to, you have your two parallel plates that do in left and right direction, these plates that I'll change it in the up and down direction. You can create a photon anywhere you want on this screen. All you have to do is control the voltages on these parallel plates. Yeah, Cedric. Yeah, exactly. Because of how fast all this happens, you can totally reverse the pole and it'll only take like fractions of a fraction of a fraction of a second, right? So now let's say they do this like crazy fast, all right? And every time you shoot a beam here, it actually produces a beam of light on a screen. And then you're looking at this, here's your eye, and you're looking at this because this is what a TV used to be. What you see is a whole bunch of photons hitting at different spots really, really fast and forming an image and changing really fast, forming a moving image, which is like a video for you guys, right? So that gigantic device, tiny screen, gigantic device was what a television used to be back when they first invented TVs. It's pretty stupid now that we think about it because it's so complicated and large. So here's another diagram of that. So it gets deviated one direction and another direction, and you get to have all these patterns. But essentially, this is what that is, right? So here is what we call a cathode ray tube. This here is a cathode ray tube, and this here, just this top part, is the part that you're looking at when you're watching TV, right? And this entire thing here is the box of the TV. So the TVs were wider than they were large, which is just crazy now that you think about it. It used to be like you look at that thing and you're like, wow, that's a giant, clunky old crappy TV. But back in the day, like a TV, like it was the size of this furniture, for you to have it was this big. It was really nonsense. Yeah, that's a cathode ray tube. All right, that's what CRT stands for. We got way better at that. Now we can individually control these things called light emitting diodes. We'll learn about them when we do circuits, or LED lights. So a screen like this is just made of a bunch of lights that we're lighting on and off using a computer program. Okay, that's the difference between what's happening there and what's happening there. That seems like a lot more complicated because you got to do a lot more things, but electronically, that was a lot easier than this. This requires programming. All right, so now let's take that and do a problem with it. Okay, I'm going to show you how to do this one, and then I want you guys to work on examples, and then that'll take us to the end of class. Essentially, here's what I want you to understand. So here is an electron. Okay, this electron is starting on the negative. There's a positive here, and so therefore it's going to get attracted towards the right. And on the right of this, there is a slit. So right there where my pen is, right, there is a slit that's going to allow the electron to pass through and enter another set of electric fields in which projectile motion is going to happen. And here there's going to be a force upwards, giving it an acceleration, and therefore you can calculate this deviation here, okay? So this deflection here, not necessarily the angle, but the deflection, okay? That's what this is showing you. I want you guys to do this problem. Here, how is that? Do this problem and ask me if you have questions. I'm going to pass it around. And then once you've done this, take out go back to Moodle. There is a parallel plate electric field problem that I want you guys to practice with as well. That'll